Welcome to the presentation of our work with the title Sailor, which stands for Scaling Anchors via Insights into Latent Object Representation. In our work, we indicate that the LiDAR-based 3D detectors exhibit severe object size domain bias. This bias stems from the invariability of the object sizes within a dataset. We observed that the average object size heavily depends on labeling policy or geographical location. For instance, the Waymo dataset is captured in the USA, where an average car is a pickup truck. On the other hand, Kitty is a European dataset where a small sedan is the most common car. The difference between the object sizes of the two datasets is obvious in this plot on the right. The size bias is the most evident in cross-domain validation. In the figure on the right, we evaluate the model trained on Waymo on the Kitty dataset. We found numerous examples like this one, where predicted object, in this case indicated in blue, is discarded as a negative sample due to the low intersection over union score with the ground truth object depicted in green. State-of-the-art approaches exploit target domain object sizes. They scale ground truth objects from the source domain to match the size distribution of the target domain. Such weakly supervised approaches are then utilized in the unsupervised domain adaptation. Instead of matching the distribution in the sample space, Sailor directly adapts anchors to the target domain. We achieve similar effect as weakly supervised methods, but in a fully unsupervised manner and without any retraining. Sailor starts with a model trained on the source data and anchors psi optimized for the same data. We iterate through the source data and compute object predictions for each frame. During inference, we store pooled feature vectors from the predicted objects in a reference feature database. After we populate the reference feature database, we fit a Gaussian mixture model parameters to the data using the expectation maximization. Given the fitted parameters, we utilize the likelihood function to estimate the fitness of an arbitrary feature vector to our reference feature database. Next, we start the anchor calibration phase. Using the same model, which is trained on the source data, we iterate through the samples from the target domain. To estimate the target optimal anchors, we slightly perturb the source anchor's psi by a small value epsilon. We then extract the pooled feature vector for each prediction. The likelihood of the features, computed with the perturbed anchors, gives us feedback on the quality of such anchors for the target data. The idea is the following. If the perturbed anchors are too large, the feature vector is going to include more background points. However, if they are too small, we are going to leave out valuable cues. The likelihood is the highest if the anchors are just right. We utilize this information to directly optimize the anchors via differential evolutions. We leave all other parameters unchanged. For more details, please check out our paper. In our evaluation, we report substantial gains in cases where the object size bias is large. In Waymo to Kitty case for the class car, we improved the baseline roughly 2.5 times and show better performance than all weakly supervised methods. In cases where the two datasets share similar anchors, such as nuisance to Waymo, there is not much to optimize with Sailor. However, it is important to note that in such cases, Sailor does not degrade the results. We report similar findings for other classes. To repeat our experiments, please check out our GitHub repository. Thank you for your attention.